Okay, so the last speaker of this session is Simon Mitton, University of Mitton, Simon Mitton, University of Cambridge. He is going to tell us about the Big Bang versus steady states, with these rivals in cosmology. Please.
Right. Thank you very much. I am not a professional historian. I've got a physics degree, and I've been a science writer and had a long career as a publisher, as a few people in this room are already aware, because I published you. So I like to speak in terms of people, their circumstances, where did they come from, what's their background, and then how did they interact with each other, and what motivated them. So you will see I will be talking about people rather than the specifics of their papers. And I've got four kinds of people. There's the three pathfinders: Einstein, Wilhelm de Sitter, and importantly, Georges Lemaitre. We've got two observers who are absolutely crucial in this story for data on realism about looking at objects in the universe and what they could find out. We've got the three musketeers, Gamow, Hoyle and Ryle, and I identify two jousting tournaments which they have. You will notice that I do not have Gamow versus Ryle. That is because neither of them met each other, and they didn't correspond. Some of this you've heard already, so I'll be very quick. 1905, we have Einstein's four papers. The road to general relativity was long and difficult. And so far as I can see, it wasn't until 1913 when Einstein learned and adopted Riemannian geometry and tensor calculus that he began to make rapid progress. In July 1915, Einstein met up with David Hilbert. Einstein knew that Hilbert was trying to find field equations as well. And in the course of this meeting, it seems that Hilbert realized he needed to get on with his program, which was not identical to Einstein's. And that led to a sort of desperate race against time for Einstein, who was worried that David Hilbert would get there first. So on the 25th of November, 1915, Einstein read his paper on the gravitational field equations in Berlin. Now, in some of the popular accounts of this, you will read that Einstein was close to a nervous breakdown and so on and so forth. He was also dressed in formal evening dress, as they did in those days in workshops like this at the Prussian Academy. 5 days after Einstein had completed and submitted his paper, Hilbert published a note giving the field equations, but in terms of priorities, the big difference between the two is that Einstein gave his proof, whereas Hilbert did not. Now, there's many solutions to the field equations, as everybody in this room is very familiar with that. Einstein in 1917, he is the first to apply the field equations to the entire universe. Now, in terms of what we've just been hearing about Bohr and so on, this is in some ways rather remarkable that Einstein is now going to apply it to the whole universe. Of course, he has to make assumptions about parameters. So Einstein produces a model which has no pressure, in other words, no radiation, but it does have matter. He didn't straight away consider its stability. It is a model which is unstable. Wilhelm de Sitter he decided to look at a universe model which did not have any matter but did contain the radiation, and his solution too had difficulties. In 1922, Friedman in St. Petersburg, he is the first one to publish dynamical solutions, and he publishes them in Zeitschrift für Physik. He finds a solution in which the universe is allowed to expand and where it's allowed to contract. He makes no connection whatsoever to astronomy. The main impact, immediate impact, which he had, is that George Gamow, who was in St. Petersburg in 1922 and took Friedman's lectures, this is when Gamow first becomes interested in general relativity. The big step forward comes in 1927. Georges Lemaitre had been working on general relativity, self-taught, from probably 1919. And as part of Belgium's post-war recovery, he was given a big travelling fellowship to spend 1 year at the University of Cambridge working on general relativity with Eddington, followed by another year in Cambridge, Massachusetts, working, for example, at Harvard College Observatory, where he came across observational astronomy and so on. By 1927, he had derived solutions for the time evolution of the radius of the cosmos. In other words, the expansion of the universe. Out of loyalty to his country, he was very much a Belgian nationalist. He decided to publish this in the Proceedings of the Brussels Scientific Society, which is a journal that was circulated to libraries and so on worldwide, but it had very little readership outside Belgium. So nothing happened for a while. Then in 1930, he wrote to his former tutor, or his former mentor, Eddington, and Eddington suddenly gives him a lot of support. Eddington described Lemaitre as being the most talented student he had ever had, and he regretted immediately that he hadn't noticed the 1927 paper. It made such an impression on him that he got Lemaitre to London. Lemaitre spoke at the Royal Astronomical Society in 1930, and this resulted in the publication of his paper in translation in the monthly notices of the Royal Astronomical Society. The importance of that is the monthly notices had a global circulation through the British Empire and so on and so forth. And so very, very quickly, Lemaitre's ideas catch on. He did another very high-profile lecture talk in 1931, which was connected with the British Association for the Advancement of Science. And so this is when a wider public begins to learn of Lemaitre's work. We were just hearing about Einstein's approach to realism and so on and so forth, and he was at a Solvay conference. This was the 1927 one. Lemaitre, of course, wasn't invited to things like the Solvay conference, but Lemaitre managed to meet up with him in a coffee break, as it were, and said that he liked the mathematical elegance of Lemaitre's work, but as a piece of physics, it was abominable. Lemaitre did recover from all of that, and he recovered from it by promoting his hypothesis in picturesque language as a fireworks universe in which everything has a singular origin and it explodes with enormous violence, and so on and so on and so forth. The impact of this in terms of quantum cosmology is Lemaitre is the first one to find an application for quantum physics in cosmology. He was the first quantum cosmologist. He applied the phenomena of radioactivity and the uncertainty principle to the origin of the universe. Now let's do a bit of realism and consider the two people who found evidence for the recession of the galaxies. The first one is Vesto Slipher of the Lowell Observatory in Flagstaff, Arizona. He uses a 24-inch telescope with a spectroscope, and he starts to look at the spectra of spiral nebulae. There's a bit of a backstory here which is helpful to know. The Lowell Observatory is named after Percival Lowell, who was a Bostonian Brahmin, a person with a great deal of wealth, and he set up this observatory in Arizona and appointed an astronomer, went and observed there very occasionally himself. The purpose of the observatory was to search for life on Mars, and Lowell himself published 3 books, the third of which is all about the economic and social system which exists on Mars. So this is the person who was Vesto Slipher's boss. Why was Vesto Slipher looking at spiral nebulae? Because Lowell believed that the spiral nebulae were nearby planetary systems in formation, which was not an unreasonable hypothesis. Well, when Slipher measured the redshift of the spectral lines in the Andromeda Nebula, he realized straight away that it must lie outside our own Milky Way system. He went on with this program of measuring the spectra of spiral galaxies. He was in contact with the Lick Observatory, which was the other observatory in the US where this work could have been done, and they had a 36-inch telescope, and they wrote back to him and said, you'd better be correct in what you're saying, because we've been unable to reproduce it, and basically you're going to make yourself look a complete fool. Anyway, the complete fool published data on 25 spiral galaxies, got the gold medal of the French Academy of Science in 1919 and the gold medal of the Royal Astronomical Society in 1932 for this work on measuring the velocities of galaxies and showing that they were in recession. Edwin Hubble, he was looking at the Andromeda Nebula as well, but from a different point of view, and using Cepheid variable stars, he was able to establish its distance and find that it was far, far beyond the Milky Way. He and his colleague or assistant, Milton Humason, by the middle of the 1920s, they had measured the distances to 40-odd spiral galaxies. It was in 1929 that Hubble does the first of his velocity distance diagrams. These are linear plots in which the velocities, almost all of them taken from Vesto Slipher, and quite a few that Hubble used. He did not give any credit to Slipher for them. So the velocities basically came from Slipher, and the distances came from Hubble and Humasson's measurements of plates taken with the 100-inch telescope at Mount Wilson. In the version of this diagram that was published in 1929, there were only about 14 or 15 points, and only an optimist would have suggested that it was possible to put a straight line through them, which is what Hubble did. But then he went on and got this, more accurate one. Interestingly, to me, Edwin Hubble never, ever claimed or accepted that he had discovered the recession of galaxies. He maintained, right until the point at which he died in 1953, that there could be other explanations for the redshift phenomena apart from the recession of the galaxies. Now, when we get to the Hubble Space Telescope, there's an enormous publicity operation going on at NASA, and they put out a great deal of information, misleading information, about how the telescope was named after the person who had discovered the expansion of the universe. In 1936, in the last sentence of Hubble's book on the nebulae, he says that he dismisses as airy speculation much of what is being talked about, and advises that this airy speculation will only cease when there is a lot more data. Already by 1936, Hubble and the people at Mount Wilson were hoping that there would be a larger telescope, and vague discussions about what the 200-inch were already underway. Lemaitre's quantum cosmology, Lemaitre publicizes this through talks and so on, and came up again with this picturesque expression of the universe having actually existed for all time, but existing just as a primeval atom which contained all of the matter and all of the energy, and it suddenly started to decay radioactively because of the uncertainty principle. He was the first person to use what was known as the Hubble diagram to actually derive an age of the universe. Very interesting character. And with the expansion of a very hot, energetic universe, he realized that there should be something left over, and he thought that the cosmic rays might be the relic of the fireworks universe, and he spent the last 10 or 15 years of his life working in cosmic ray physics. Okay, now I come to the three protagonists. George Gamow, theoretical physicist, born in Odessa. He had an absolutely terrible time. He lives through two revolutions in 1917, and then there is the rise of Stalin. There's also the Civil War in, I think, 1922, 1923, and he writes about that in one place in an interesting context. He's preparing for the examinations at the end of his first year studying physics at Odessa University. And he says that 4 blocks away, he can hear the White Army and the Red Army fighting from house to house, just sort of down the road, and he just carried on working. In 1923, he leaves Odessa and he goes to St. Petersburg. His father sold the family silver to get the money to enable him to go to St. Petersburg. And there, his career in theoretical physics absolutely takes off. He's influenced, as I said, by Alexander Friedman. He's also interacting with several young men who became very well known. For example, Lev Landau. And 1928, in order to improve his knowledge of the new physics, he went to Göttingen. He also got permission of the Soviet authorities to spend time in Copenhagen with Bohr's Institute. This is where he made a discovery that, as the historian Helga Krag puts it, just, but only about just, should have won him a Nobel Prize. This was the quantum mechanical tunneling, allowing a particle to penetrate a potential barrier to either get into a nucleus or get out of the nucleus. We know from Gamov's memoirs that this whole idea, from conception to writing a paper and sending it off, took him less than a week. He became increasingly dissatisfied with Soviet Russia. Stalin forbade the teaching of anything whatsoever to do with quantum mechanics in the Russian universities in St. Petersburg. This, of course, was because everything Soviet was predetermined. In 1933, the Solvay Conference, Gamov participates in the 1933 conference, and he decides that he will go to America and work there and not go back to Mother Russia. Right. So I'll now come on to Fred Hoyle's early life, which is easier to deal with. Bingley, West Yorkshire, a lovely accent which he employed to very great effect in the late 1940s and early 50s with his radio broadcasts. And his father signed up World War I, enlisted, machine gun corps, served 4 years, came back alive, survived the Battle of the Somme. According to Fred, what his dad told him was, he survived the Battle of the Somme because it was very, very misty, moisty morning, and he just told the 5 guys he was responsible for, don't fire anything, don't fire in the direction of. And they survived because that's what they did. He went on to read mathematics at Cambridge. His first doctoral supervisor was Rudolf Piles, nuclear physicist, who went off to Birmingham. Hoyle then had Paul Dirac, who was in the same college as him. A lovely arrangement. Fred felt he didn't need any supervisor, and Paul Dirac felt it was beneath him to supervise students. So that relationship worked very well indeed. And Fred was appointed a JRF at St. John's in 1939. Then his wartime work was research on radar for the Admiralty, and that's where he met Bondi and Gold, about whom I'll have more to say in a moment. In 1945, he returned to his teaching in Cambridge. Now, Martin Ryle is very different to either of these. A radio engineer and became a radio astronomer. He came from a really distinguished family that could trace their origins to being serious estate owners, farmers, in the reign of Elizabeth I. His father became Regius Professor of Physics at Cambridge. Gilbert Ryle was his uncle, so on and so forth. Ryle was educated at a fairly exclusive private school and went on to read physics at Oxford from 1936 to 39. September 1939, he joins the Cavendish laboratory in their radio group. But after only 8 months, he was signed up to go and work on radar countermeasures, particularly the design of antennae by the telecommunications research establishment, and so his war service was all done there. He had a really traumatic time. He'd only been running his group at the age of 23 for a few months when 3 or 4 of them, who were testing equipment that Ryle had designed in a Halifax bomber, the bomber crashed and killed everyone. And Martin never ever completely recovered from the trauma of this. Now, how to connect the war work with radar and cosmology? Hoyle devised a method of measuring the altitude of an incoming fighter attack plane to make measurements, observe from the ship, and be able to get not only the direction, but also be able to get the altitude and the distance. You needed both of those, of course, in order to take protective measures. Hoyle was, as it were, mentioned in dispatches for the great effect of the pencil and paper method he devised, which could be used in real time at sea. And at the weekends, as is very well known, he, Bondi and Gold discussed cosmology. Ryle, his antenna designs and his designs of receivers and detectors was very important when he got back to Cambridge in 1945, because he was able to start straight away on radio astronomy and observing the sun. Gamow had an easy ride because he had been a major in the Soviet army teaching teaching meteorology. He was denied security clearance. So when George Washington University was cleared out of all the nuclear physicists who went and worked on the Manhattan Project, he was basically left twiddling his thumbs and working on the formation of galaxies. Gamow had been interested in the origin of the chemical elements from the 1930s, and had published 2 or 3 astrophysics papers. The quantum mechanical tunnel effect, he realized fairly quickly this would give you a method of building the elements by them absorbing protons, neutrons, whatever, and building up the periodic table. Gamow decided not to do any research on this. He gave the ideas away to others who went on to show that maybe you could get nuclear reactions going. Yes, right. In a flash of inspiration, he proposed that Lemaitre's primeval atom could be where there would be the right conditions in terms of energy and heat, in terms of energy, for getting neutrons to be absorbed by the nucleus. And he promotes this from 1942. The idea was made to work by his doctoral student, Ralph Alpher, who first of all demonstrated that a cold Big Bang didn't enable you to achieve very much because everything was over very quickly and there simply wasn't enough energy content. Alpher then began working on his own on a hot Big Bang model in which the neutrons in the early universe would have sufficient energy to be able to penetrate the nucleus. And for good measure, he calculated the present-day temperatures as 5 degrees K. Gamow was never interested in the slightest in this, and in later years he tried to get Alpher to drop it. Crucial test of Alpher's model was, did it reproduce the actual observed reality of the abundances of the elements? And this diagram is taken directly from the thesis itself. As far as I can make out, nobody has ever showcased the actual diagram in the thesis before. So you're the first. You can see the jagged line going up and down. Those are Goldschmidt's natural abundances, and all the other stuff in the diagram is Alpher showing on an overly complicated diagram how all of this could work. And he established cosmology as a real branch of physics. Unfortunately for him, Gamow grabs all of the publicity. The initial paper, Gamow says the authors are Alpher, Bethe, and Gamow. Bethe had nothing whatsoever to do with it. That was just false. Then he organised a grand parade in a room like this for Alpher's doctoral examination. And invited 300 people, including the press, and arranged for the Washington Post to have, and the New York Times, to have nice stories saying that Gamow and his student had found that everything in the universe was made in 5 minutes. Fred was the real pioneer of nuclear physics. Fred didn't believe anything about Gamow's synthesis in the Big Bang. It all happened too fast. So Fred's contribution was that by 1946 he published a seminal paper saying that the origin of the elements could be accounted for by these particle fusion processes at a temperature of 3 billion degrees in the center of red giants. Crucially, Hoyle published this paper before Gamow and Alpher published their model of nucleosynthesis. Needless to say, Gamow had no time for Hoyle's paper because Gamow claimed to have already proven that you couldn't make the elements in an equilibrium, a slow equilibrium process, which is what Hoyle's was. So Hoyle, Bondi, and Gold, their steady state universe, which is 1948, after Fred's nucleosynthesis paper, Gold asked the question after watching this extraordinary movie, which you can loop continuously, what if the universe is like this? And the three of them and said, well, let's just work it out. Let's just do the physics. How would it work? And so that's how the steady state theory with the continuous creation of matter actually began. And the way in which the steady state theory could be tested against the Big Bang is very easy to understand. In a Big Bang universe, the objects that you observe now that are a long, long way away, you're seeing early in the life of the universe. Therefore, they will not look the same, they won't be perhaps distributed in space in the same way as the objects that are nearby. The whole point about the steady state universe is that the universe itself never evolves. It just expands and new matter is created in the void, and the new matter then makes galaxies and so on and so forth. So no matter where you look or when you look, it always looks the same. The acid test was going to be, does the universe evolve? And Martin Ryle is the person who set himself the task, as it happened, of testing this. He and his colleagues began constructing radio antennae for observing initially the sun, but then for looking at radio emission generally. We're in the late 1940s, which I like to refer to as the heroic age of muddy field astronomy. They set up their first. There were Ryle and Graham Smith, two future astronomers royal. Neither of them knows any astronomy at this stage in their career. They're setting up the antenna, and this is a Michelson interferometer. And with an interferometer, you can get the positional information of the radio sources in the sky. And so Ryle began to make the Cambridge catalogues of radio sources. His first catalogue had about 50 objects. The second catalogue had about 120. The whole time there was this nuisance, Fred Hoyle, snapping at him and saying, well, I've got all these ideas, I can explain all of that. Very nice of you to have got all this data and dealt with horses trampling your cables and so on, but I can tell you what it all means. Well, Ryle was never having any of that. So the first result, the first dispute between them was when Ryle started saying he had discovered radio stars. And Hoyle, the consummate nuclear astrophysicist, said they cannot conceivably be stars, and that was their first big dispute. From his surveys, Ryle, with his radio stars, he remains convinced that these objects are all inside the Milky Way. Now, this isn't terribly surprising because two of the objects were supernova remnants, and so certainly some of them were, but not the Gold and Hoyle pressed Ryle to say these must be distant galaxies of a completely new kind, and this irritated Ryle sufficiently that he was able to get Gold off the scene and dispatch him to the Royal Observatory and be a nuisance there. Ryle also became very distressed in 1952 when Bader and Minkowski measured the redshift of the radio galaxy Cygnus A, and as he said later, I realised to my dismay that we were in the cosmology game, and he didn't really want to be there. The big clash is to do with the counts of radio sources. Now, Ryle's first two sets of observations, there was insufficient data and they weren't correctly analysed, so it was easy for Fred Hoyle to say, you haven't proved anything. You haven't proved anything at all. We could just as well be in a steady state universe. Third survey is looking good, but Hoyle won't have any of it. He's saying by then, well, this man, his first two were rubbish. Why should I take this one seriously? So for the fourth, Ryle had a publicist. This sounds a bit like Gamow with Alpha's thesis. Ryle had a publicist, set up a press conference in a room like this. Ryle's here, showing all the results. Fred is sitting over there under a spotlight, staring at his shoes and wondering what's going to happen next. He got the shock of his life when at the end Ryle says, and now, gentlemen, Fred Hoyle over here is going to tell all of you why I am completely wrong. And Ryle sat down and Hoyle rushed out of the room. So that was one of their very big clashes. All of this steady state and Big Bang becomes resolved very suddenly in 1965 with the discovery of the cosmic microwave background radiation. So the relic radiation is found. The theorists at Princeton University immediately realize that what has been found is the radiation which Alpha had predicted. However, so much time had gone by that those few people who did remember it thought it was Gamow who had pronounced or predicted the 5 degree K radiation. He never did any such thing, and it took a long time for Alpha to get the proper credit. The proper credit didn't really happen until the end of the 20th century. But the discovery of the background radiation was absolutely the end for Fred Hoyle's steady state theory, although he didn't accept it very readily. He never accepted it. He was always looking for something else. And so one of the I'm going to give you one conclusion which is a bit different to what you'll see elsewhere. These feuds over the origin of the elements and the nature of the universe and so on, these feuds were acted out in public, and it was the first time that had happened for astronomy. Both sides were maximising their use of the media, newspapers, broadcast media, and quite recently, in a letter which Gamow wrote to Ralph Alpha in 1955, 3 pages of it, there was a curious thing in the margin, and I turned this round, and there was a little cartoon diagram, and Gamow is just saying to him, hook up yesterday with Hoyle, BBC, NBC, I gave it to him real good and won. And that is the only fragment of evidence that we have that the two of them publicly disagreed with something, and Gamow thought he'd won. Anyway, I'll leave it there for now. Thank you.
Thank you very much for really interesting talk. Is there any questions? Second from the back in the middle, please.
Two questions. You said that Einstein praised the mathematical elegance of Lemaitre's paper but called it abominable physics. So if he praises the elegance of the maths, how does he justify calling it abominable physics? And the second question was, you mentioned it was suggested that Gamow should have got the Nobel Prize for quantum tunneling only just. What did that mean? What did that mean?
Well, I'll answer both of those questions. If I may, I think the answer to your first question perhaps was given elegantly in advance in the last talk, in that Einstein had much stricter discipline on how to model the world than Gamow. Gamow was very much for being very speculative. Sorry, Lemaitre. Yeah, with Lemaitre, Einstein just didn't accept a physical model in which the entire universe begins from a singularity. Right? So on your question on Nobel Prizes, this can only be dealt with in a sense by personal opinions. People like Helga Krag, who I turn to as my go-to source, because Gamow didn't settle down and work through the implications of this model, he simply blabbed about it to everyone and let them all go away and work out the implications. There was no follow through. In the case of Hoyle, who did not share in the Nobel Prize for nuclear astrophysics, when Tony Hewish, Jocelyn Bell, and so on, the discovery of pulsars, which is a very well-known story, Hoyle wrote a letter to the Times saying that Tony Hewish had stolen his doctoral students' ideas and data. Now, 2 or 3 days later, Hoyle realized that he'd made an absolutely terrible mistake by criticizing a colleague in the academy in those terms, and and so on and so forth. The opinion of people who have been close to Hoyle, of whom I'm one, is that he just completely disqualified himself. He'd written, he'd written a letter saying the Nobel Committee didn't know what they were doing. So I think I've answered both of your questions. Okay.
The gentleman on the right, from me.
With regards to the almost Nobel Prize, in fact, it was turning that whole idea around to get the alpha particles into nuclei, or rather protons into nuclei, that Cockcroft realized, and then of course the Cockcroft-Walton accelerator was built because of that.
That's right, yes, yeah. Gamow realized very quickly that the process he was describing was reversible, but what you've just said very helpfully that's another example of how he didn't follow through on things.
In the middle, gentleman in the middle. And then the very bottom next.
Thanks. And thank you for the talk. I enjoyed the spoiler alerts. You said that when Ryle unveiled the results from the 3C catalogues, that
yes.
Hoyle basically did a runner, didn't respond at all. Why didn't Hoyle come back with an argument basically along the lines that the catalogue just doesn't sample enough of the universe? We don't know what distance these go out to, and so you can't say anything about whether the universe evolves or not. This sample's too small.
There was one respect in which the sample, the third and fourth, the samples were large enough because the parameter that was looked at was something called the log n log s diagram, which is basically
the inverse 3 halves.
That's right. Yeah. it wasn't showing 3 halves. It was showing 1.8. So yeah.
Okay. Thanks.
It's the log n log s diagram.
Hello. Thanks for a fascinating talk. You mentioned Gamoff's colleague Alpha, did you say?
Yes.
So Alpha computed elemental distribution.
Yes.
Happening at the Big Bang.
Yes.
And then, as I'm aware, Hoyle proposed the alternative stellar synthesis.
Yes.
So but if I saw that correctly, Alpha's distribution agreed very well with some published
yes.
data. So what happened with that information? Was it kind of felt to be still useful?
Alpha continued to work on the theory and improving the theory for a further 5 years. But the reason why it would ultimately fail is because the time period in which everything had to happen was less than 30 minutes from the start of the universe to the point where it's expanded sufficiently that you can't get any further nuclear reactions taking place. That was one difficulty. The other difficulty is that, which was faced by both theories for some time, not having any stable nuclei of 5, 6, or 7. This was something called the mass gap, which you've got to get through it. The way in which Hoyle got through it was he said, well, actually, I'm not going to begin at the beginning. I know stars contain loads and loads of carbon, so I'm going to start with carbon and see what happens if alpha particles merge with carbon in the interiors of very hot stars. So he had a different approach altogether.
Very clever. And of course, people began looking at the supernova
Yeah.
formation of
Heavy elements. Thank you.
Is there any questions? I think it's very good time for coffee and tea. Let's thank the speaker again.